Einstein's Relativity, the Special Theory and the General Theory. Chapter 8, The Concept of Time in Physics. New Modern Translation 2025. Albert Einstein and Harry Yoon, Translator. Introduction, Chapter 8. Welcome to the wonderful world of Einstein. Einstein did not start to revolutionize our view of the world. Einstein did not plan to change our fundamental notion of space and time. He was just interested in understanding electromagnetic phenomena, and light in particular. He was just focused on understanding nature in the way that truly made sense to him. As Einstein explains in the preceding two chapters, chapters 6 and 7, the theory of electromagnetism, as formulated at the time, was in conflict with the existing physics, e.g., the classical mechanics of Galileo and Newton. In particular, Maxwell's theory of electrodynamics was not consistent with the Galilean principle of relativity. In the previous chapter, for example, he illustrates that the law of constant speed of light was not compatible with the classical velocity addition formula. Einstein just wanted to resolve these apparent conflicts. But as it turned out, this effort ultimately led to exploring the fundamental conceptions of space and time. Special relativity ultimately turned out to be a new and revolutionary theory of space and time. For the following three chapters, starting from this chapter, Chapter 8, The Concept of Time in Physics, Einstein explores the very concept of time and space to the extent relevant to the special theory of relativity. In chapters 8 and 9, he introduces the concept of relativity of simultaneity, and hence, relativity of time. In chapter 10, he then introduces the concept of relativity of distance. At the end of chapter 3, Einstein states, hence, the description of motion in mechanics can only be complete when we have a proper definition of time, so that these time values can be viewed as physically observable quantities by virtue of this definition. Then, Einstein gives an exemplary definition as to how time can be, or should be, measured in the context of classical mechanics, e.g., using the moving train and falling stone example. The most important point of that definition is that time must be defined, measured, and used with respect to a particular reference frame. Now, in this chapter, Einstein goes further to define time more precisely by taking into account of the fact that light propagates at a finite and constant speed, among other things. In order to do this, he first deconstructs the common idea of simultaneity, and then redefines it so that it is consistent with the special principle relativity. This story continues in the next chapter. One thing to note is that the adverb simultaneously and the phrase at the same time in English have exactly the same meaning. And yet, there can still be some subtle differences in nuances between them. The German word for simultaneous is gleichzeitig, which contains the root zeit, time. It will be helpful if you keep in mind that simultaneity is about time when you read this chapter. In some places, we repeat the essentially same phrases, simultaneously and at exactly the same time, even in the same sentences to emphasize this fact. This is really the first chapter in this book that can be truly considered relativistic ideas. The concepts presented in this and the following few chapters were all the original ideas of Einstein, which nobody else had thought of, even among the people who had been working on the related problems at the time. As we mentioned before, special relativity is not an easy theory to understand at a fundamental level, despite the misconceptions to the contrary. Having an open mind, and even being humble, is often the most important prerequisite when learning new ideas. Chapter 8. The Concept of Time in Physics. Let us once again go back to our railroad embankment, with a straight, and possibly infinitely extended, railroad track. Suppose now that two bolts of lightning have struck the railroad track at two distant locations, A and B, along the railroad embankment. At this point, after observing the flashes of light from this lightning occurrence over the railroad track, I make the following assertion. These two lightning strikes at A and B occurred exactly at the same time or simultaneously. If I now ask you, my dear reader, whether this statement makes sense to you or not, then you will most likely answer my question with a decisive, yes, of course. But if I now press you with an additional question to explain to me the meaning of the statement more precisely and clearly, then you will slowly start to realize that the answer to this question may not be as simple as it appears at first glance. After some reflection, however, you may come up with an answer like the following. The meaning of this statement is pretty clear in and of itself, and this statement requires no further clarification or explanation, except that, of course, I may have to give some additional considerations in a particular case in practice. That is, if I am given the task of determining by observations whether or not the two events in the particular case actually took place at the same time, or simultaneously. But I cannot be entirely satisfied with this particular answer for the following reason. Let's suppose that an ingenious meteorologist claims to have discovered a new law of nature by some clever reasoning, which can be stated as follows: bolts of lightning must always strike the two locations A and B simultaneously. Then, even before we evaluate its truthiness, we will first have to make sure that this statement itself, of such a theoretical prediction, indeed corresponds to reality. This argument applies in general to all statements of physics in which the concept simultaneity plays a role. For the physicist, the concept or idea, such as simultaneity, only exists if it is possible to find out whether the concept corresponds to reality in a specific case in reality. A definition of simultaneity is therefore required, so that the definition provides the method by which the simultaneity of two events can be determined through experiments in the real world. In the present case, for example, we can decide using such a method whether or not the two lightning strikes indeed occurred at the same time, or whether or not the two lightning strike events were simultaneous. As long as this requirement is not satisfied, I am deceiving myself as a physicist, of course, also even as a non-physicist, if I believe that I can attach a meaning to any statement of simultaneity. Read no further, dear reader, until you admit to me with conviction that you understand and agree on this point. After some more reflection, you now make the following suggestion for establishing simultaneity in practice. The distance of the connecting section AB between the two locations A and B is measured along the railroad track. An observer is placed in the middle point M of this section AB of the track, and he is provided with a contraption, e.g. with two mirrors inclined at 90 degrees to each other, which allows him to visually watch both locations A and B at once. With this setup, if he perceives the flashes of the two lightning strikes at the same time through this contraption, then they are simultaneous. I am rather pleased with this suggestion, but I still do not consider the matter to be entirely settled. Now I raise the following objection. Your definition would be certainly correct, that is, if I already knew for a fact that the light which signals the lightning strikes at A and B to the observer at the midpoint M travels at the same speed along the path A to M as along the path B to M. Testing this condition would only be possible, however, if the means of measuring time were already available, which depends on the definition of simultaneity. It thus appears as though you are going in a circular logic here. After some further consideration, however, you give me a somewhat slighting look, and rightfully so, and explain to me. I still maintain my definition that I just gave, since in reality it does not assume anything about light. There is only one requirement that the definition of simultaneity should satisfy. That is, it must provide, in every real-world case, an empirical decision as to whether the concept to be defined, i.e., simultaneity in this case, is fulfilled or not. It is indisputable that my definition satisfies this requirement. That light takes exactly the same time to travel through the path A to M as through the path B to M is in reality neither a presupposition nor a hypothesis about the physical nature of light. But it is just a stipulation which I can freely make at my own discretion in order to arrive at a reasonable definition of simultaneity. It is clear that the definition above can be used to give an exact meaning to any statement of simultaneity. Furthermore, it can be used with regards to the simultaneity of not only two events, but also across any number of events, regardless of how these events may be located with respect to the reference frame, e.g., the railroad embankment. This definition of simultaneity, or the same time, therefore leads us to a definition of physical time as well. To define time, let us suppose that three identical analog clocks are placed at the points A, B, and C of the railroad track on the embankment, which is being used as a reference frame, and they are calibrated in such a manner that their hands are at the same corresponding positions at the same time, in the sense described above. That is, they are all synchronized. The time of an event is then understood to mean the time indication, the position of the hand, of one of these clocks which is spatially closest to the event. In this way, each event is assigned a time value, which can be observed, at least in principle. This definition of time also relies implicitly on the following physical hypothesis, the validity of which cannot be doubted in the absence of any empirical evidence to the contrary. It is assumed that all of these clocks run at the same rate if they are identical to each other in every aspect. Or to put it more precisely, if two identical clocks which are arranged at rest at two different points with respect to the given reference frame are set in such a way that one hand position of one clock is synchronous with the same hand position of the other in the sense above, then the same hand positions of the two clocks remain always synchronous in the sense of the definition above. Translator's notes. This chapter is written in a more or less dialogue form. This can be viewed as a minor influence of Galileo. Obviously, it was Plato over 2,000 years ago who wrote pretty much all of his books in a dialogue style. Galileo also favored this writing style. As far as the translator is aware, Einstein wrote one semi-technical article in a purely dialogue form, Dialogue on Objections to the Theory of Relativity, 1918. In this chapter, interestingly, the reader who he appears to talk to is in fact a proxy to Einstein himself. Now, this is the beginning of the real story. As Einstein mentioned in the previous few chapters, the conflict between classical mechanics and electrodynamics optics, as related to the principle of relativity, will be resolved by deconstructing the traditional concepts of space and time. This is the first chapter along that direction, in which Einstein starts to address the physical concept of time and clock. If the reader has been goofing around so far, then this is a very good time to get a new fresh start. We have 10 more chapters to go in part 1. Time to start paying a bit more attention now. A quick summary. When we state that two events occurred at the same time, or simultaneously, what do we mean exactly by this statement? The concept of simultaneity was taken for granted as self-obvious, but our traditional understanding of this concept was really imprecise. For one thing, if somebody says that two events occurred simultaneously, how do you empirically verify this assertion of simultaneity in practice? We do indeed need an exact definition of the concept of simultaneity in such a way that any assertion related to simultaneity can be verified or falsified in reality through an experiment. There has been no such definition, other than the not entirely correct presumption that there exists some kind of universal time which is the same across the entire universe. We propose the following procedure as a physical definition of simultaneity, or that of two events at distant locations, A and B, occurring at the same time. The distance of the connecting section AB between the two locations A and B is measured in a straight path. An observer is placed in the middle point M of the section AB along this path, and he is provided with a contraption which allows him to visually watch both locations A and B at once. If he perceives the light signals from these two events at the same time through this contraption, then they occurred simultaneously, or they occurred at the same time. Now, this definition appears to have a problem because we seem to be assuming that the speed of light from A to M and the speed from B to M are the same. One can object to this, since such an assumption cannot be made until there exists first an exact definition of time, and hence our definition seems to be circular. But this is not an assumption. It is, in fact, just a stipulation which we are entitled to make. We only need one reasonable definition of simultaneity which can be used in practice, and our definition satisfies this requirement. This definition of simultaneity then provides an operational procedure for synchronizing clocks, which in turn leads to a physically measurable definition of time, with an additional but totally reasonable assumption that all identically made clocks run at the same rate. Now, time can be assigned to an event as follows. Let us suppose that n identical clocks are placed at n points along the axis of a one-dimensional frame of reference. They are all synchronized in that their hands are at the same corresponding positions at the same time, as defined earlier. The time of an event is then understood to mean the time indication, the position of the hand, of one of these n clocks, which is spatially closest to the event. In this way, each event is assigned a time value, which can be observed in principle. Einstein's frame of reference. The concept of inertial reference frame, as we know it now, was invented at the end of the 19th century, at the time of Ernest Mach and his contemporaries. It's not clear when it became mainstream, but it's very likely that it was after special relativity was accepted as a part of the standard physics curriculum. Einstein uses the Cartesian coordinate system as pretty much the same as the reference frame in this book. In fact, Einstein gives the credit to René Descartes for the invention of the reference frame, in the modern sense of the word. In Chapter 2, he introduces the concept of the frame of reference, or the Cartesian system of coordinates, as a generalization of the idea of an idealized rigid body of reference, with respect to which spatial locations can be specified, using three coordinate values. Then in Chapter 3, Einstein relates motions of material bodies to reference frames, as in motion is relative. This inevitably leads to the conclusion that time must be defined and used relative to a frame of reference as well. At the end of Chapter 3, he uses one clock for each reference frame to measure time. In this chapter, he now explains the necessity for using multiple clocks relative to a given reference frame, due to the fact that light travels at a finite speed. Then he goes on to propose one way to synchronize these clocks again, based on his new definition of simultaneity, while relying on the fact that light travels at a constant speed. Figure, clocks distributed in an inertial frame. According to Einstein, therefore, a frame of reference looks like the coordinate system shown in the preceding figure. We assume the existence of a rigid body for reference, implicitly, to which the coordinate system is attached. The axis of space represents the coordinates of the three-dimensional space, and the arrow of time shows the direction of time. That is, by convention in relativity, time always flows vertically upward in this kind of diagrams. Note that space and time are assumed to be infinitely extended in this depiction. Time, for example, starts at the infinite past, and it will continue forever. Space likewise has no boundaries. We just draw a relevant, often unspecified portion of space and time in these diagrams. As noted before, geometry only dealt with space before Einstein. Newton introduced time as a separate and independent entity into physics. It was Einstein who first incorporated time into the coordinate system, or the reference frame. That is one of the reasons why we use the term Einstein's frame of reference in this notes, to refer to the reference frames with clocks. A few years after the publication of Einstein's 1905 paper on special relativity, Minkowski made it into a neat mathematical formalism, Chapter 17. But as far as special relativity is concerned, Minkowski's four-vector formalism does not add anything new to physics. In essence, Minkowski treated time and space almost equivalently, by elevating Einstein's clocks to the time axis of a coordinate system. In Einstein's frame of reference, clocks are placed, which may be viewed as imaginary, at various places in the 3D space. In the above figure, they are placed along the space axis, and only a few of them are shown, because of the limitations of these diagrams as just alluded. Note that these clocks need not be placed uniformly, or at equal intervals in this one-dimensional example. Nor do they have to be placed infinitely densely. The lightning thought experiment. As is well known, and as we have already mentioned a few times, Einstein was famous for using thought experiments so effectively as his scientific discovery tools. That was also the case with Galileo. If the reader has chosen this particular book to learn relativity, say, rather than other more standard textbooks, because it is written by Einstein himself, then it will be worth your time to play along with Einstein while reading this book. The lightning thought experiment described in this chapter is one of the most famous such thought experiments by Einstein. We will continue to use this idea in the next chapter to show that the concept of simultaneity is relative. There are a lot of misconceptions about thought experiments. Many people seem to think that a thought experiment is only useful in situations where real experiments cannot be performed. That is not entirely correct, although thought experiments can be surely useful in those situations. But a thought experiment is, or can be, much more than that. The real world is complicated and messy. Thought experiments can be used to pick and choose, so to speak, what is important and what is not important for a particular physical phenomenon. For example, in the real world, a hammer falls much faster than a maple tree leaf. This is due to air resistance, which Galileo realized is not essential in understanding the phenomena of free fall. In fact, the air resistance complicates the situation. For this reason, among others, people now believe that Galileo's famous experiment at the Leaning Tower of Pisa was most likely a thought experiment. As alluded earlier, we primarily care about the propagation of light in empty space. In fact, Einstein sometimes explicitly mentions this, e.g., Chapter 7, but most of the time it is implicit. In the context of special relativity, the speed of light almost always means the speed of light in empty space without air. You cannot really remove air in a large scale, and hence every scenario that we talk about in the context of special relativity is pretty much a thought experiment in principle. Air does not slow down light very much in practice, but it is rather important to conceptually understand this distinction. The light equation. Many readers should be familiar with this concept. Hence, we will defer more basic explanations to the appendix. A spherical light wave propagates in a vacuum at the constant speed, c, in every direction. Hence, the propagation of the spherical wave of light in time can be described by the following equation in the x, y, z coordinate system with time coordinate t. X squared plus y squared plus z squared equals c squared t squared. Figure, the equation of light and the light cone. Now, in a space with one spatial dimension, x, this becomes a line in the tx coordinate system, as shown in the figure above, a. X squared equals c squared t squared. On the right-hand side, b, this drawing has been made a bit prettier. This kind of curves or surfaces are known as light cones. In a two-dimensional xy space, a spherical light wave becomes a circle, and the overall form the light wave in the txy coordinate system appears as a cone, or a double cone. Hence the name, which is used regardless of the dimensions of the underlying space. Why is light special? After the publication of the special theory of relativity, there were a lot of objections and criticisms and backlashes, as one can easily imagine, since Einstein's theory appeared to be too bizarre. One of the most common criticisms was the various roles that light seemed to be playing in the development of his theory of special relativity. For example, Einstein uses the light signals emanating from certain locations to define their simultaneity, as explained in this chapter. Why use light? Why is light special? Or is it? In his original 1905 paper on special relativity, Einstein uses the law of the constant speed of light in vacuum as a separate hypothesis, in addition to the hypothesis of relativity. This is purely due to a historical reason. At the time, it wasn't entirely clear whether the phenomena of electrodynamics and optics should obey the principle of relativity, chapters 5 and 7. In this book, which was originally written in 1916, for example, Einstein does not state that the law of the constant speed of light is in some way special, besides the fact that it is just one of the laws of nature, albeit one of the simplest laws. Einstein never claimed in his life as far as we know, that light was in any way special in the context of special relativity. In some sense, however, the speed of light, that is, the speed of light in vacuum, is special because it is, or it seems to be, the maximum speed of signal propagation in our universe. We will further discuss this later in this note, as well as in Appendices B and C. People all seem to have different opinions on this. As far as we are concerned, at the risk of sounding like a crackpot, it is really an open question whether light plays any role in the construction of space-time. Einstein's strange world. Special relativity describes a certain imaginary world. For the lack of a better word, we use imaginary, but it does not mean it's not real. It's a very peculiar world. In a way, it's a mathematical world. We are not simply referring to the strange phenomena here that are predicted and verified in the framework of special relativity, such as time dilation and length contraction. Those are more or less taken for granted at this point. Einstein uses a world that we don't actually see or feel in his special theory of relativity. For example, in Chapter 2, he builds a frame of reference, in our terminology, using rigid sticks and whatnot. Obviously, you cannot build such a rigid framework or scaffolding in the real world. In fact, according to this very theory, the special theory of relativity, rigid bodies in the sense of Newton do not exist, as we just mentioned. Also cf. Chapters 1 and 12. This becomes even more real in the context of general relativity, according to which space can be warped and twisted and so forth. So what is this imaginary rigid body of reference that Einstein uses to formulate his theory? This is just one example. We do not want to overload the reader with too many advanced and possibly confusing concepts. But we will provide some clues as to what exactly is Einstein's world throughout the book, in our notes and comments, for a small number of the readers who want to go deeper into the theory of relativity, beyond this introductory book by Einstein. For instance, we provide our explanation of the so-called Andromeda paradox, which pretty much everyone seems to get wrong, again in our view, in an appendix of the next chapter. But at the end of the day, in a way ironically, you will have to learn general relativity if you want to truly understand special relativity. In any case, if you are reading the translator's notes and appendices, and not just Einstein's main chapters, watch out for some clues that we provide in particular in the next few chapters. Just keep in mind while reading this book that the wonderful and strange world of Einstein only exists in your mind, in your thoughts. Correspondence with reality. We used the word abstract before to refer to the frame of reference, for instance. But this again does not mean that the world that Einstein describes is purely mathematical. As a matter of fact, that is far from true. All results of special relativity have been experimentally verified in the real world, Chapter 16. Furthermore, as mentioned before, Einstein was a hardcore empiricist. Even in this book, he emphasizes the importance of empiricism, starting from chapters 1, 2, and 3, e.g., for the definitions of distance, time, and motion, and in fact throughout this book. In this chapter, he also states that, with regards to the concept of simultaneity, we need a definition that can be used in practice. For the physicist, the concept or idea, such as simultaneity, only exists if it is possible to find out whether the concept corresponds to reality in a specific case in reality. The only important requirement of such a definition is that we should be able to determine, given two specific events in reality, whether these two events are simultaneous or not according to this definition. Otherwise, a given definition is in no way unique. What is time? Time is the most elusive concept in fundamental physics and philosophy. We quoted the following statement by St. Augustine before. What then is time? If no one asks me, I know what it is. If I wish to explain it to him who asks, I do not know. The concept of time seems to have some parallel to that of heat. For over 2,000 years, since the time of ancient Greece, people could not figure out what heat was. Most philosophers assumed that heat was some kind of fluid, which flowed from a hotter region to a colder region. Even the early pioneers of thermodynamics like Carnot, Joule, and Clausius regarded heat as a material fluid. It was the physicists like Maxwell and Boltzmann, in the second half of the 19th century, who ultimately figured out what heat was based on the atomic hypothesis. Obviously, at this point, everybody knows what heat is. Now, will time turn out to be a rather simple concept as well when, and if, we finally crack its secret? The word time, as used in English, is a very complex and confusing concept with many different meanings and connotations. First, time means a point or instant in time. For example, if somebody asks, "What time is it?" to you, then you would reply with an answer like, "It's 8 p.m., which really means 8 p.m. of a certain very specific day and month, etc., according to the calendar and clock that we all use. This more or less corresponds to Newton's absolute time. Second, time means a time interval or duration. When we say it's been a long time, for instance, we are indicating a long time interval, since a certain moment in time, which is implicit, unspecified in this particular statement. In a sense, as we will see, this is often the most relevant meaning in the context of relativity. In addition, time can mean the flow of time, with all its different connotations such as the direction of time and so forth. For example, we all get old or older. We all are, as of today, different from us 10 years ago. This is mainly because time has passed. Physicists are also particularly interested in a particular aspect of time, which they call the arrow of time. Time can be divided into three parts, namely the present, the past, and the future. But how exactly is it divided? How does the future become now, and how does now become the past? Time is such a complex subject that we will have to dedicate an entire book or two only to scratch its surface. But one thing to note is that there is an essential aspect of time that does not generally get much attention. That is the rate of the flow of time, which, alternatively, or more concretely, can be viewed as the rate in which the clock runs through time. Einstein mentions this at the end of the chapter, as one of the two hypotheses which he has used as a basis for his definition of time. In a way, this is one of the most important components of time, which lies at the basis of the interval of time which we just mentioned. We will further comment on this throughout this translator's notes. Time is also intimately related to the concept of ordering of events, the concept of causality, and so forth. But we will not discuss them here. What is a clock? A clock is a device that measures time, and time is what is measured with a clock. This is often said as an irony, or as a joke, because they are circularly defined without really being defined, like the chicken and egg problem. But truly ironically, this is indeed the best definitions that we have with regards to time and the clock. That is, nobody knows what they are. As far as Einstein is concerned, he seems to be of the opinion that the clock comes first. For example, in this chapter, Einstein suggests that the time of an event is the position of the hand of an analog clock. So what is the clock according to Einstein? Identical clocks. At the end of this chapter, Einstein states that his particular definition of time depends on the following additional hypothesis. All of these clocks run at the same rate if they are identical to each other in every aspect. Then he goes on to explain what he means by this statement, in terms of the positions of the hands of these identical analog clocks. You can go back and read it again if the meaning of this statement is not clear to you. We will wait for you here. So what does this statement mean? First of all, a clock as used in this statement must have at least one hand. Many typical analog clocks that we are familiar with tend to have 2 or 3 hands, e.g., an hour hand, a minute hand, and a second hand. But that is not required. In fact, Einstein's analog clock can have 1,000,000 hands. But we will simply assume that each of these clocks has one hand, for simplicity. Einstein does not explicitly state it, but clearly the assumption is that the hand of a clock moves, that is, the position of the hand changes over time. Then we have a clock. Take a moment, and make sure that you agree that there is no other requirement to define a clock. To imitate Einstein in this chapter, read no further, dear reader, until. Now, we do not use 1 or 2 clocks in isolation. We need many clocks distributed over a given inertial reference frame. The requirement is that all these clocks used should be identical. And now we are back to the above-mentioned hypothesis. Identical clocks run at the same rate, regardless of where they are placed. Note that the phrase "at the same rate" is used to refer to the collective behavior of the clocks, across all these clocks, and not for one clock. That is to say, the hand of a clock does not even have to run uniformly. For example, the minute hand of a real clock that we use moves more or less at a constant pace, e.g., 6 degrees every minute, but that is not required. The hand of an Einstein's analog clock can move in any way, clockwise, counterclockwise, fast, slow. But all the clocks that we use must run at the same rate. That is, their hands all have to move exactly in the same manner. Newton's absolute time. We mentioned, albeit indirectly, that Newton's concept of time was one of the most misunderstood concepts in physics. Maybe this is a good time to revisit this issue. We described earlier a few different common meanings of the word time. When we refer to Newton's time, the most immediate thought that comes up is the fact that in Newton's world, there exists a global time, that is, a clock time that is the same in the entire universe. We now know that that is not completely true, according to Einstein. But more importantly, in Newton's conception of time, time flows at exactly the same rate everywhere in the universe. This is a mere consequence of having a global time. But regardless, this is one of the most ignored aspects of Newton's time. Now, this is exactly the same as Einstein's hypothesis that we just discussed. That is, despite the common misconceptions, the change from Newton to Einstein as far as time is concerned is relatively minor. We still live in a world where all identically constructed clocks run at exactly the same rate regardless of where they are located. The relatively minor change in our conception of time, according to Einstein, will be presented in the next chapter. Just be reminded that in Einstein's definition of time, time is defined with respect to a particular reference frame, whereas such a notion does not exist in Newton's definition. Why does the definition of simultaneity lead to the definition of time? Einstein first defines the concept of simultaneity, and then defines time based on this concept. This can be confusing to some readers, partly because of the apparent difference between the words simultaneity and time in English, as we mentioned in the introduction. E.g., the words simultaneity and time don't seem to be related to each other in their appearances, whereas the corresponding German words do. Simultaneous refers to two or more events happening at the same time. But it can also refer to the fact that the times of two or more events are the same. Note the subtle difference. The second meaning is more relevant in the current context. To elaborate a little bit more on this point, suppose that we have two Einstein's analog clocks with one hand each. For illustration, suppose that the hand of each clock is continuously rotating around its clock face at a certain same rate, and that we are interested in a particular event in which the hand points exactly to the north, or it is at the 12 o'clock position. Now, the condition of simultaneity of two such events for the two clocks means that the time readings of the two clocks, T sub 1 and T sub 2, respectively, are the same, that is, the two clocks indicate the same time. If you have to use equations, then T sub 1 equals T sub 2. Or using the time interval delta t between the two respective events. Delta t equals T sub 1 minus T sub 2 equals 0. Now, here's the amazing thing. If delta t equals 0 at one time, that is, if any two clocks indicate the same time at the same time, then it will remain to be delta t equals 0 for all future times, that is, these two clocks will always indicate the same time. This is because of the aforementioned hypothesis that identical clocks run at the same rate. If n clocks are, therefore, synchronized with respect to a particular reference frame, then they will all remain synchronized indefinitely with respect to the same reference frame. Hence, we have a consistent definition of time, which is the same across a given reference frame at all times. Einstein's strange frame of reference. In Chapter 2, Einstein introduces the concept of a coordinate system attached to a rigid body of reference, which we translate to a frame of reference. Although he initially starts with rigid sticks, etc., but he immediately acknowledges that the coordinate system is ultimately an abstract or semi-abstract concept. For example, how do you specify the coordinates of a certain cloud floating above your town square? You cannot really build a framework that extends to the cloud, for every cloud for which we need the coordinates. Now, not sure how many readers have thought about this, but how do you specify the position of Jupiter, for instance? Extending a long pole even to a cloud is not really practical. Then, how do you determine the 3 coordinates of Jupiter at a given moment? And what moment, considering that even light takes a finite time to reach Jupiter? What about Alpha Centauri? What about the Andromeda Galaxy, which is some 2.5 million light-years away? How long would it take to build a scaffolding with rigid sticks in practice that reach the Andromeda Galaxy? Now it becomes even more strange when we consider time. According to Einstein's scheme, we need to place many identical clocks everywhere, spatially, in a given reference frame. How would you do that? On top of this, we will need to synchronize all these clocks. How long will it take to synchronize a clock on Jupiter and another one here on the Earth? How long will it take to synchronize 2 clocks, one on the solar system and the other on Alpha Centauri? What about the clocks in the Andromeda Galaxy? Figure, a few identical clocks distributed over a reference frame. Once they are synchronized, they remain synchronized. But how do you synchronize them all in the first place? One-way speed of light. At the end of the chapter, Einstein's doppelganger objects to the proposal of the reader, who really represents Einstein himself, regarding the proposed notion of simultaneity. Your definition would be certainly correct, that is, if I already knew for a fact that the light which signals the lightning strikes at A and B, to the observer at the midpoint M travels at the same speed along the path A to M as along the path B to M. Testing this condition would only be possible, however, if the means of measuring time were already available, which depends on the definition of simultaneity. It thus appears as though you are going in a circular logic here. The objection is that our formulation of time seems to be circular because the definition of time, or of the same time, depends on the definition of speed, which in turn depends on that of time. Then the reader, aka Einstein, responds as follows. That light takes exactly the same time to travel through the path A to M as through the path B to M is in reality neither a presupposition nor a hypothesis about the physical nature of light. But it is just a stipulation, which I can freely make at my own discretion in order to arrive at a reasonable definition of simultaneity. This is possibly one of the most confusing parts of special relativity. Did you understand the objection raised by Einstein's doppelganger? And Einstein's answer? Einstein made the same stipulation in his first 1905 paper on the special theory of relativity, which caused so many objections and criticisms. Over 120 years later, there are still people who claim that special relativity is wrong because of this problem, e.g., the one-way speed of light. We will leave this question to the readers if this kind of puzzle interests you. Just keep this question in mind so that you can think about it once in a while when you have a chance. And that's the most fun part of doing physics. What's next? Now that we have a definition of simultaneity that can be empirically tested, we will discuss its relativity in the next chapter, which is really a continuation of this chapter. Chapter 9, Relativity of Simultaneity. This concept of relativity of simultaneity ultimately leads to that of relativity of time. The kinematic phenomenon known as time dilation will be introduced in our appendix of Chapter 9. Einstein explains this concept in Chapter 12 using the Lorentz-Einstein transformations. This book is not available on Amazon.